for joining me. I can't wait to get started with this talk, and I'm going to go right into it because there's a lot to cover. So this talk kind of all started as a lot of my talks do, and that's when I talked to my husband. My husband's also a developer. He's actually an architect at Amazon, and when we get to talking about all kinds of nerdy things, we talk about problems at work. And one of the things that really struck me was the sheer number of transactions that he actually gets to work with every day. Not everyone gets to work with that kind of scale. We're talking about like hundreds of thousands of transactions. So fast forward to all of the things that we talk about that related with that. And one of the biggest things that came out of that conversation was how if you're running at that kind of scale, or you have that many concurrent requests running at one time, you definitely have to think about idempotency. That is the one serverless principle to rule them all. And so a lot of people, including myself, had trouble when we first heard this. I'm like, first of all, you're like, how do you pronounce this? Is it idempotency? It's idempotency. And by the end of this, I'm pretty sure you will know how to say it and know what it means. So super quick agenda, we're going to go item what, because there's a really interesting background behind where this word actually comes from. And then we're going to talk about why this principle, idempotency, actually works really well hand in hand with serverless architecture, in particular good serverless architecture. Then we're going to go into something that's very common and very related with this, and that's doing safe retries. And finally, we'll look at a couple tools and libraries that I think are pretty cool that either help you achieve idempotency or have it built in, or really encourage idempotency when you're building things. So item what? So if you look at the word idempotency, this is actually not a real word, at least according to Merriam-Webster. In fact, when I Googled it, the word that actually shows up in the dictionary is idempotent. And according to Merriam-Webster, their official definition is relating to or being a mathematical quantity which, when applied to itself under a given binary operation, equals itself. But in the great words of Kevin from The Office, why waste time, say lot word, when few word do trick? I did not like that definition. It got me a lot more confused just trying to go through it. So I actually like Random House Webster's definition much better. It's much more succinct, and that's unchanged when multiplied by itself. So idempotent is really a mathematical definition. It's a property that exists, and it's usually used to describe multiplication, right? Whenever you multiply something, the same two parameters, you usually get the same result. And so when you keep that in the back of your mind and you understand this definition, it's now easy to see the co-opted tech definition of idempotency. So in it, we describe idempotency as a characteristic that ensures when running an operation over and over and given the same input, which that part kind of maps to when multiplied by itself, that the same output is achieved every single time, that it's unchanged. And so as almost all things, it has a math background. When we have used this to describe how we build our applications, or how we should build our functions or write our code in an idempotent way, this is what we mean, that no matter how many times we run it, even if it's an infinite amount of times, as long as we're using the same inputs, we should be able to reliably get the same output. We should get the same result every time it is run. So idempotency, that's what this means. It's this characteristic that allows us to get unchanged results no matter how many times we run it, every single time we run it with the same input. So at this point, you're like, great, Adrienne, what does idempotency have to do with good serverless architecture? And I'm going to be one of those people that answers a question with another question. And I'm going to say, have you heard about the 7 design principles of well-architected applications? So for some of you that have, great, you're going to see kind of where this talk is heading towards. But if not, that's okay. I'm going to talk to you about it super quickly because that's not the focus of this talk. But we'll get just enough so that you understand why it's important to idempotency. So these 7 design principles of well-architected applications, they are not from me. They are shamelessly stolen or borrowed from AWS's architecture guides. And in particular, they have a lot of really, really good guides that have these kinds of things in play, best practices, principles. And the ones I'm about to share with you are the ones that are through a serverless lens. So they actually have different sets of principles based on the context or lens with which you're looking at it through. And so super fast, the 7 are speedy, simple, singular. So it's following the single responsibility principle, right? You make things focus, you do things one at a time, you minimize execution time, you do additional processing through a queue instead of waiting. Second one is share nothing. So unless you're using a specific library that does this for you, you have to assume that your functions in this case, when we think about serverless, that they're stateless. So just assume that they're brand new, that you have to explicitly state and load everything that you need every single time. Assume no hardware affinity. So there's a reason a lot of people choose serverless, right? And that's because you don't necessarily want to deal with all of the hardware configurations that may come with that kind of granular configuration. So when you try to use dependencies or even write your code, you want to try to do it in a hardware agnostic way. And then you want to use events to trigger transactions. So again, you want to get more comfortable with asynchronous operations, right? A lot of us are used to very synchronous operations where we do something, we wait for the server to give us back a response, and then that whole action is done within one specific amount of time. But we want to try to think around that and use events to trigger transactions to help us facilitate asynchronous actions where we don't necessarily have to wait for everything to be done right at that moment. And we also want to think of concurrent requests, not total requests. So a lot of people try to minimize the amount of total requests that are being done, when really, if we want to take advantage of the scale that's given to us, if we use something like serverless services, then we want to think about concurrent requests. We want to make the work that we're spreading apart and fanning out to be as agnostic as possible so that we can take advantage of that and have multiple computers, multiple servers work on it at the same time. We want to orchestrate our application with state machines, not functions. So this is particularly talking about not wanting to invoke functions from other functions. You want to use something like step functions or even Jonah's durable functions to do this for you. And last but not least is design for failures and duplicates. So as we've quickly gone through these 7, almost all of them are affected by idempotency, this characteristic that you want to make sure that no matter how many times you run a piece of code, you send a request, that the result that you get is the same. But while almost all of them are somewhat related to idempotency, the most important one is this one right here, and that's designing for failures and duplicates. To me, it's the most important one because this is the one that's impossible to do without idempotency. And so we'll talk about that, why that is. So when we're designing for failures and duplicates, when you think about this principle, it's kind of peculiar that there's one that's completely dedicated to both, right? This kind of acknowledges that failures are going to happen, anomalies are going to happen. Even Werner Vogel said himself, things always fail all the time, or paraphrasing, but failure is acknowledged, it's going to happen. So that's why it's especially important that if we're aware of this, if we know that this is going to be a constant in building applications, that we need to design a system that incorporates idempotency for these two things. This is because failures almost often lead to retries. So sometimes the edgiest of edge cases, they're usually solved by just rerunning the thing, right? We retry a lot of things. We recompile, we turn it on and off again. A lot of the weirdness or the transient errors that we get that we can otherwise not debug are usually solved by just retrying it. And there's nothing wrong with this solution. In fact, it's been solved, or it's solved so many issues before, and it's been a proven effective solution to so many of these random errors and transient issues that a lot of SDKs have started to build it in by default. They have a lot of default retry behavior that's a part of the SDK. So we can go down like an even more granular rabbit hole of things like exponential backoff, which is depending on how many times you retry, you wait a little bit before doing it again. You can talk about jitter rates, which is something similar, and all of that. There's a lot of different things that you can reconfigure with retries, but we won't go down that rabbit hole. But the point to remember here is because we know failures will occur, and because we know retries are something that is a possible effective solution, we're going to have them. And so now that we know we're going to have retries in our toolbox, implementing retries means duplicates can and will occur. We're the ones that are telling our code explicitly to re-invoke an event. We're rerunning it. We're explicitly telling it to try again. And we are responsible for introducing the duplicates into this system if we implement some sort of retry behavior. So no matter how many depending how many times that we configure this retry behavior, we can retry a reasonable amount of time all the way to an infinite amount of times, but let's not do that. So understanding that we're going to retry means we are going to introduce duplicates. So again, holding on to that fact that we know duplicates are going to occur. If we know duplicates exist, then idempotency is the key we need to mitigate side effects. So we've introduced these duplicates. It's now our duty to make sure that we pair it with idempotency to make sure these duplicates are not leading to these side effects. So side effects. Take a little break here. What are these side effects? What are these things that I'm talking about? Well, let's take a look and see what happens without idempotency. Tell you a quick story. My husband and I are driving home from a road trip. And while in transit, I want to order a cake because if there's anything I want people to know about me, it's that I love desserts and cake is awesome. So why not, right? So I open up my trusted cake shop's website. It's called Freed's Bakery. It's a really popular cake shop here in Las Vegas. And I start browsing. So I'm looking through, all of them look really, really awesome and delicious, but who am I kidding? I'm going to get the same thing. I'm going to get the world famous strawberry shortcake. So that's when I start to fill in my order details. So when we think about the workflow that's about to happen here, just set some baselines here. There's me, Adrienne, the person who's going to place the order, and then we have where the workflow really begins, which is the website, the client in this case, and let's say an API. This is where the rest of the services may be. Maybe there's an ordering service, an invoice service, etc. But for the purposes of the story, this is what we're going to deal with and what's important. And as you can see by the downward moving arrow, time is flowing in that direction. So we have the typical setup here. I'm going to order my cake. And once I submit my order, it's going to place that order. The website's going to say invoke an order placed event. Now, if you remember a little bit before when we were driving home, we were about to approach a tunnel. And so it's right about at this moment where I actually enter the tunnel. And not too long after, I lose signal. Not uncommon, this happens all the time, but unbeknownst to me, my order actually reached the server. It actually got to Freeds. They're actually processing that order and they're making that world famous strawberry shortcake. So because I'm still going through the tunnel though, I don't know this. I don't have a signal. All that's happening right now is me looking at my phone, waiting to see if my order has processed. Now this tunnel's finally coming to an end, and so we exit out the other side. Once this happens, presumably I regain my signal, right? And then at this point, the most likely thing that will happen in this scenario is that I'm going to see some sort of error, right? I'll regain connection, and we're hoping that the website either says the order wasn't placed, or sometimes I'll just see there's like a connection timeout or a socket error or some sort of error that pretty much tells me, hey, the order that I just placed, it actually didn't go through like you thought. And so when this happens, I'll see that error and I'm going to resubmit that order because I'm going to get my cake. So same thing happens. I order the cake, the order is placed, Freeds processes it, confirms that it's being processed, and awesome, cake is on the way. But let's hold on a minute. Let's zoom out in this particular workflow. If you remember earlier, this order, the one we placed before entering the tunnel, because the requests are not idempotent, that order actually got placed as well. And so, surprise, I'm not getting one cake, I'm getting 2 cakes. And this is exactly one of the biggest side effects, one of the biggest problems of duplicates in a system that are not idempotent. In this scenario, the intent of the requests that I'm making, they're not captured anywhere. So because it's not captured anywhere, when these requests reach the API, they have to take it at face value, right? The server has to take it at face value. It doesn't know that I mistakenly ordered 2. It thinks I really want to order 2. And depending on how you look at it, that could be a good thing or a bad thing that I'm now getting 2. But the intent, my original intent, was that I wanted to order a single cake. And so even if we had retry behaviors in place, let's say I didn't manually resubmit and manually do this retry operation, all of those subsequent requests that are made fall to the same side effect, that they are not capturing the intent. And so that's the biggest side effect to remember here, is that duplicate requests are considered valid requests if the requests are not idempotent. So now that we see why this is a problem, again, we can continue to argue that it may not be a problem. You can think of it, if it's easier to think about paying twice or 3 times or 4 times for a bill, maybe that's easier to see that it's a problem, because multiple cakes are never a problem for me. But if we now see the problem here, we're now probably thinking, how do we then apply idempotency? How do we make sure those requests are idempotent? And so there's a few elements that were missing from that previous workflow that are now needed if we want to make these requests idempotent. So to me, I think it comes down to 3 things. The first thing is something called an idempotency key. So this is the unique identifier that's usually generated by the caller, the person making the request, the thing that is invoking an event, everything that we want to be known about that request, the intent that I keep talking about of what that request actually means, this is the idempotency key. So this unique identifier could be an event ID, it could be a client ID, it could be a client token, it could be a hash of parameters, it can be a whole bunch of things, but generally it is some sort of UUID. It's a unique identifier that tells us this is a very specific request. The next part is an idempotency layer. So now that we've captured the intent of the request with our idempotency key, we need to do something with that intent. We need to do something with these requests. And so this idempotency layer is what acts kind of like a filter. It decides what to do with our requests once it receives it. So in a web request scenario like the one that I've shown, that could be sitting on an API layer, for example, some sort of middleware on the API. If it's on some kind of messaging queue, it could be on the consumer of those messages, where again, it's deciding what to do. So we need some sort of idempotency layer that does something with these idempotency keys. And the last part is some sort of persistent storage. So in order for the idempotency layer to work, and in order for the keys to make any sense, we need to store all of the things that have been happening with our application somewhere. So usually this persistent storage is some kind of immutable log of events, or not immutable, but a log of events. Sometimes it's append only is what I meant to say. And it keeps the current state of things. It sort of acts as the source of truth for all of the idempotency keys that we have seen. And it also, depending on how we implement it, can be a list of checkpoints in the retry mechanisms that occur. So in, for example, the durable functions that Jonah spoke about before me, the orchestrator actually checks against an Azure storage table. And even if something fails in between, what it does is it goes back and replays all of the events that have happened up to the point of failure. So that is the persistent storage part. It stores the state, it's the source of truth for the keys, and it can act as a list of checkpoints in retries. So these are the elements of idempotency. So how do we now include this? How do we add that as part of, let's say, our last workflow so that we can make those requests more idempotent? Well, let's go back and see what that would look like. So there's me, Adrienne, and we're going to order some cake from Freed's, And as our first step, the application needs to generate some sort of unique identifier for our requests, right? So again, this could be anything, but generally it's some form of UUID. So let's say this has been generated. Freed's has helped generate this UUID. It's now going to place it in my order. So just as a sample place order call that's going to be made, and we're going to add that idempotency key as part of my order details. And now we're going to go ahead and place that order with my idempotency key and send an invoke that event, basically. Now, in our new idempotent workflow, we have our idempotency layer sitting in our API. And we also now have some persistent store that keeps track of our state of all of the orders that are happening with Freed's. So now, instead of just directly going to process the order, the first thing that's going to happen is we're going to check our persistent store to see if there is that key there. It says, hey, I got this new request. There's this idempotency key in here. Do we have this? Have we seen this one before? If nothing is found, then we can more safely proceed and then go ahead and run that place order handler. So at this point, this can continue on to go over to the order processing. They can accept it, they can confirm it, go on the merry way. And once that has been completed, we then now set that idempotency key as well as the result of either that confirmation or whatever has happened at the handler. And that's that. And if you take a second and look at this quite basic workflow, but idempotent workflow, you can already see that this is far better than the workflow that we had previously, where there was no idempotency built in. In fact, if we just assume, let's say we go back in time and this was the workflow that we did, and this was that initial request that I placed when ordering in the tunnel. At this point, we don't receive a response, right? Because I'm in the tunnel and I have lost signal. Well, at this point, it's going to be okay, because now that we make any subsequent requests, let's say I resubmit, or let's say it's even better and there is some default retry behavior and the application is making those subsequent requests for me, we go through the same process. All of the subsequent requests are going to go through the same thing and go ahead and place that order. It's going to have that same idempotency key, though, because it's me still ordering it. And then it's going to check that idempotency key in our persistent store. Except this time, now, because we have stored that key in our persistent store and we actually have a result, we're going to know that it exists. It is something that we have seen before. And instead of going through and running another place order handler event and giving me more cakes than I bargained for, we're just going to return the initial result from the initial request. And then that response is going to be sent over to me, and that's going to be great, because that's what's most important here, is that the original intent has been captured. That even though there may have been 2 or more subsequent requests, that our idempotency layer and our persistent store was able to kind of determine that, hey, these are actually duplicate requests. We don't want to continue and place all of these different orders. We just want to do this one, the one that we have successfully run and the one that we have seen before. And so in this way, you can see an idempotent workflow is far greater and very much mitigates the side effects that result as of duplicate requests. So the last thing I want to talk about, now that we're all excited about idempotency, maybe you can see that I really, really like this principle, is I want to talk to you about a couple libraries and tools. Specifically, I'm going to go very in-depth in one because I think they have a lot of really cool features, and then I'm kind of just going to list some of the other ones that are worth looking into at your own leisure if you want to learn a little bit more. So the first thing I want to show you is the AWS Lambda Power Tools repo. So this is a really, really awesome library that actually implements an idempotency module. Now, unfortunately, they only have an idempotency module for Java and Python. They do have a TypeScript one, but they're just starting out with that, and the TypeScript one does not have the idempotency module, but keep an eye out for it. So this one does have the idempotency module in Java and Python. And it's really neat to see that a lot of the things that I've talked about here can be easily seen here. So for example, the idempotency key that they use here is actually a hash representation of either the entire event that you may be sending with your Lambda or a specific configured subset of the event. So you can configure just a few portions of the payload to be your idempotency key. And of course, the persistent storage that they use is Amazon DynamoDB. Right now, it's the only supported one. Hopefully they change that, but don't bet on it. And as an example, you can start quickly initializing, or you can start quickly using this by initializing a DynamoDB persistence layer. This is a Python example. So you'll see here that you can use it with an idempotent decorator on your Lambda handler. You can see that on line 8. Some of the cool features I want to tell you about that this library helps you, specifically the idempotency module, helps you prevent multiple Lambda handler function executions on the same payload during a time window. So you can set a period of time that says, hey, consider these as duplicates or not. And depending on if it has the same payload, it will take care of it for you the way that we did in our workflow and say, oh, these are actually the same requests. We're not going to continue further. This ensures that the Lambda handler returns the same result when it's called with the same payload. So very similar to the workflow I showed. If it has seen it before, it's just going to return the same result if it's the same payload. You can reuse the same DynamoDB table to store idempotency state. That's because it stores the function name in addition to the idempotency key for you as a hash key. And you can do something like set expiration periods for idempotency records. So all of those records or keys that we're storing in that persistent storage in the DynamoDB in our persistent storage layer, sometimes you don't want to keep all of those records, right? Sometimes you just want to keep them for a period of time. So by default, this library expires those after 3,600 seconds, or that's an hour, but you can configure that time. And so sometimes you just want to keep that there for the time that you need it and then get rid of them. Otherwise, if you keep all of those records, that can grow very, very, very large. And so this is one of those that I highly encourage you to check out because the documentation is on point. It's very thorough. It has a lot of examples, both in Java and Python, and it's the most fleshed out that I've seen. Some other great tools and libraries that are worth mentioning. The first one is the Stripe API. So they support idempotent requests and it implements idempotency keys. So if you look at a lot of APIs or even a lot of blog posts of people who try to implement idempotency, they always refer back to Stripe's API because they've just done it so well. And so these are two really, really awesome resources, both their docs and a blog talking way more in depth about idempotency that I highly recommend you check out. There's something called the Idempotent API that performs additional idempotency checks. It's a NuGet package specifically for ASP.NET Core. It implements this filter that you can use on some HTTP requests or HTTP verbs, and you can get that as a NuGet package, and this blog post talks way more about it. There's obviously step functions. Now, while they're not idempotent in nature, they help you build idempotency in with the way that they are built, and they're very similar to durable functions, which with deterministic orchestrators, which make them idempotent, you can easily build idempotent requests with this. And so again, check out the docs on both AWS step functions and Azure durable functions if you want to learn more, and you can obviously ask some questions too. So thank you, more Serverless. That is everything that I have. There's so much more I could talk about. I'm happy, hopefully I can extend this talk, but happy to answer any questions.
Thank you, Adrienne. That was fantastic. And first of all, I'm hungry. I was already hungry, and you made me really super hungry, and I definitely want some cake right now. Second of all, your slide design is amazing. I love the way you really simplified the concepts. You could teach a class on slide design, honestly. Fabulous.
Thank you.
So we do have a couple questions from the audience, but everyone feel free. We've got about 7 minutes to go, so feel free just to ask your questions and we will try to get to all of them. So Jack asks, what would be the difference between using persistent storage for idempotency and the app being stateful?
App being persistent layer and the app being stateful. Well, to me, when I hear stateful at a very generic level, that just means you're storing some sort of information about it. So they work together hand in hand. But if you want to talk about the persistent storage layer as being idempotent or being used in an idempotent way, you're pretty much using that storage layer as that log of requests that are being done. So if you don't have this storage layer, for example, there's no way for you to know, right, what requests have gone through, what actions have taken place. And so to me, as in the way that I understand stateful, that would be the biggest difference. So it's not to say that they're completely different. They kind of play with each other nicely. And they're maybe not too different, but if you want to look very specifically at idempotency, that's what the persistent storage layer would be used for.
Yeah, I mean, and I'm new to this concept somewhat, so but it would seem to me like in some ways this idempotency would be could be a very simple version of statefulness in the way that it's not meant to I was thinking, okay, we have these SDKs, for instance, that constantly tracking events, right? And I don't want to duplicate events, but it's not really stateful. I just want to make sure that this event doesn't get tracked twice, right? So I'm not using any kind of statefulness in the function other than just verifying we're not duplicating a request. right?
Agreed. That's
But
a really, really good point. The other thing I'll add now that you've actually said that is this store, right? This is not just a single store either. Sometimes you have state that's kept for the entire application, and you know every single part about it. For this persistent storage layer, let's say you have a microservices architecture, you may actually have a persistent storage layer per service or per event that you're trying to keep track of. And that's absolutely necessary. You don't want one really large one that holds all events. You want to hold one per event that is happening. So for example, you would have that one just for all the orders placed, and that would be its own persistent storage layer. If you had, let's say, assigning cooks or invoices and you're keeping track of those services, that would be a separate persistent storage layer that you would keep, because it needs to know at every step of the way what events have occurred. And so in that way, like you said, it's a very simple stateful machine that very much is narrowly focused on doing just that, keeping track of all of the things that have passed through.
okay, excellent. So Ilka asks, if a backend returns an error for a request, should you also store the failure result with the idempotency key? I'll get that pronunciation right before we're done, I think.
No worries. It became one of those, it's weird to me because I was working on these slides for so long. So that's a great question. You can store the failure depending on what you're trying to do. For the most part, you usually wouldn't store the failure, because when it does fail, you probably have some default retry behavior that's going to send subsequent requests in, and you usually mitigate that failure. But let's say you retry it multiple times and it just always fails, or something bad always happens at random pieces of the request. You can store that failure, and then it is up to your application to now say, hey, we have a valid failure on here. You want to deal with that on the application. So you can absolutely store it. You just need to make sure to take care of it if you do store it, and have a reason for storing it.
Okay, so and I guess, how much information do you typically recommend storing with each of these keys? I mean, what if the response is large? It seems like you could easily just get really, build up your database and the charges associated with it, very quickly. Like, would you have some data stored somewhere else that somehow this is connected to, or you just dump everything in this DynamoDB or whatever key value store you put it?
That's a really, really great question. At a minimum, what you want to store in these persistent storage layers are the things that you need to be able to do the request in an idempotent way. So absolutely, you're going to have the key in there, that's for sure. And at the very minimum, that's probably the only thing you can store. If you have the results in the persistent storage layer, then that is okay. But one thing that you can exercise here, again, are those expiration timeouts. So in those power tools that I mentioned, you can set an expiration time, because exactly like your question, those are going to grow astronomically if you continue to store them, and depending on the size of your payload, they're just going to grow. So if you know that you don't need to decide whether any subsequent requests are duplicates, then you can say, hey, I don't need these records anymore, they've been processed, you can delete them. And then that's another way to make sure that those don't grow. So at a minimum, keep what you need in there that enables you to rerun the requests in an idempotent manner. At the very minimum, that's at least the idempotency key. And then absolutely make sure you use these expiration timeout windows if you have them.
Okay. That's a great answer.